elements. So now we get into the galvanic cell. So a lot of electrochemistry, like I said, is going to be lab scale thermodynamics. But the tool we are going to use to do our lab scale thermodynamics is the electrochemical cell. It is a way for us to take a spontaneous reaction and separate it up into two parts, a reduction and an oxidation, shocker, and then be able to study those separately. Because you can have a reduction that is coupled to an oxidation, but it doesn't have to be always the same redox couple, right? You can take that and react it with a different one. And that's where you can do all of these cool experiments where it's like, I'm going to do this one reaction on as a reduction, and then I'm going to see all these other different types of oxidations. Or I'm going to pick one oxidation and then look at lots of different reductions. But in order to do that, we need to build a tool to study those reactions. Right? And in a galvanic cell, these are ones in which a spontaneous chemical reaction is used to generate an electrical potential. So this is like a battery. Batteries are galvanic cells. It's a spontaneous redox reaction. It's going to produce a current and a potential, a voltage, and they can do work. That's what you do with these things. Sometimes you will get a negative voltage. That just means you have misidentified which direction is the spontaneous direction for your reaction. So if I've got a reaction between manganese oxide and iron, right, and we balance it out in solution, we're going to have manganese oxide and 5 irons giving us manganese 2+ and iron 3+, right? So iron went up, it was oxidized, our manganese went down, so it's got to be the reduction. Iron is oxidized, manganese is reduced. So I did this by looking at, here's my easy one where I don't have to do any math, right? And I'm looking at this and I'm seeing, this guy went from 2 to 3, number not go down, number go up, therefore oxidized. If this guy is my oxidation, this has to be my species that's getting reduced. So look for the easy thing and then realize, hey, opposite of that. So you only find one thing and then you can find the other. All right, so electrochemistry is the area of chemistry concerned with the interconversion of chemical and electrical energy. Galvanic cells, or voltaic cells, they're called the same thing, is a spontaneous chemical reaction which generates an electric current and a potential. An electrolytic cell is the opposite of that, in which you are providing power to drive a non-spontaneous reaction. Electrical current drives a non-spontaneous reaction. You have electrodes. One is an anode and the other is the cathode. The anode is where the oxidation occurs and the cathode is where the reduction occurs. So kind of stick this in your head. Reduction happens at the cathode. It always happens at the cathode. Doesn't matter whether you're a galvanic cell and you're making electricity or you're an electrolytic cell and you're using electricity. The reduction happens at the cathode. That's what makes it the cathode, that's where the reduction happens. Okay? We're going to be working in an electrochemical cell that will be divided into 2 half cells. Just like we had a half reaction that was an oxidation and a half reaction that was a reduction, where half cells are going to contain those chemical species that are involved in each of those half reactions. And the study of these kinds of cells goes all the way back to Luigi Galvani and Alessandro Giuseppe Antonio Anastasio Volta. So 2 Italian scientists who were early pioneers in electricity, and Galvani was the one who was doing these experiments where he had a dead frog and he hooks up some batteries to it and is watching the legs jump, right? And you can see that these guys were living around the turn of the 19th century, so almost into the beginning of the 18th. And Mary Shelley's Frankenstein was written in 1818. So the idea of Frankenstein not being like horror or fantasy, but it's really science fiction, because at the time, that's where the pioneering science was. It was, here's electricity and we can do things with it. What's within the realm of possibility? And there was no reason for them not to think that you could reanimate dead tissue if you're sitting there and you're like, okay, here's a dead frog, and look at that, I can make its legs jump. So it was a very logical extension. So just like we've got movies like Jurassic Park now, which are building on contemporary knowledge about DNA, or what was it, Prey, which is the nanotechnology with the gray goo, right? Those are all extensions of what was happening at the time. And so it is very much a science fiction story. And if you really want to entertain yourselves, go read up more about Mary Shelley and the fact that she was married to Percy Bysshe Shelley and her family background as radical feminists and reformers, and the fact that they were making out in graveyards and stuff. It's absolutely fascinating. So they don't tell you that in regular high school, but go ahead and read it. All right, so to build our electrochemical cell, like I said, we're going to separate our reactions into two half reactions, into separate half cells. We're going to need to connect them to build an electrical circuit. And part of that circuit is going to be this component called a salt bridge. And it's going to allow cations and anions to move from one half cell to the other. The ion migration cations are going to migrate towards the cathode, which is marked positive, right? So in order for reduction to happen at the cathode, your positive thing goes over to the cathode. Electrons are going to hop from the cathode onto whatever species is over there, which means that the cathode itself has a negative charge, right? But it is going to be marked positive. And part of that has to do with Ben Franklin getting shit wrong way back in when he was doing stuff, because he had to guess, like, all right, I got some sort of electrical current, we'll make it positive. And he just guessed wrong and ruined life for the rest of us and engineers forever. So anions are going to move towards the anode, which is marked as negative, even though it's going to be actually electropositive. So electrons are going to build up on the cathode and electrons are going to move away from the anode. Cell potential is the difference in the electrical potential between the anode and the cathode. It's going to be concentration dependent, it's going to be temperature dependent, and it's going to be determined by the nature of the reactant. So some things are just going to give you more voltage than other things. If we look at the redox reaction, that's going to proceed spontaneously in one direction under standard conditions. So standard conditions, remember, are going to be 25 degrees C, 1 atmosphere pressure for all gases, 1 molar concentration for all liquids. If I take a solution of copper sulfate and I stick a strip of zinc in it, what's going to happen is that our copper 2+ ions are going to move towards that surface. An electron is going to come off of the zinc. My copper will be reduced from copper 2+ and plate out on the surface of the zinc. My zinc, because it has lost an electron, is going to move into solution. Because remember, anytime you see a plus charge or a minus charge on something, it has to be an aqueous solution. So it's going to move into the solution from the solid, and this is our overall reaction. Zinc solid and copper 2+ give us zinc 2+ and copper solid. And if we do that, that's a spontaneous reaction. It's a spontaneous redox reaction, but really we're not going to be able to do anything useful with that. Right? It's in one container. It's happening all at the same time. In order for us to study that, we're going to build one of these electrochemical cells where we're going to separate our two half reactions. So we're going to have our zinc in a container all by itself on one side, and we're going to have our copper and a copper electrode over here on the other side. And so now my zinc half reaction and my copper half reaction are not taking place in the same container. They're physically separated from each other. So now it's going to be easier to study. But in order to do that, right, we're going to need to allow migration of ions to complete an electrical circuit. So potassium ions in this salt bridge, which is made out of agar, or it could just be a piece of string soaked in, this one's potassium nitrate. So the potassium ions are going to move towards this cathode because that's where the cations want to go, right? By convention, we're going to put our anode on the left and our cathode on the right, so that when we measure a voltage and it's going in the spontaneous reaction, it's going to be something positive. Now, there is nothing saying physically you can't take this and step on the other side of the table and now your copper is on the left-hand side of you. right? Or I could take my electrical leads and switch them around, right? If that happens, I'm just looking at the spontaneous reaction. But if I switch the leads, my voltage will be opposite because now I'm measuring one relative to the other, but in the opposite way. So my voltage will be negative. If I just physically change my location, I'm still looking at that spontaneous reaction. It's not going to change my voltage, but it's going to be confusing because you always want to put the oxidation and the anode on the left and the reduction on the right, right? So what goes on the right? The reduction with the letter R goes on the right. It's also in alphabetical order if you want to think about it that way, right? Anode comes before cathode. Oxidation comes before reduction. Right? So now we can study those electron moving processes. So an electron is going to come off of the zinc. Two electrons are going to come off of that zinc, and they're going to go away. And they're going to go up this wire. And so the electrons are going to move through a wire from my anode to my cathode. So my cathode, which is marked with a plus sign, is going to actually have all the electrons on it, right? Once those electrons are on there, this guy actually has a negative charge. So all of the cations, brings all the cations to the yard. So my copper 2 plus sees that negative charge on the electron, migrates towards that copper surface, picks up an electron, and is reduced from copper 2 plus to copper 0. And so what will happen over time is that this electrode here will get skinnier as we get more zinc ions into solution. My zinc 2 plus concentration will increase. My cathode itself will get skinnier. Over here, so my anode will get skinnier. My cathode over here is going to build up copper, right? It's going to get fatter, but my concentration of copper 2 plus in solution will decrease. Right? And if we look at this and we look at our overall chemical reaction, copper 2 plus is a reactant. And so you would expect its concentration to decrease over time. And zinc 2 plus is our product. And we would expect its concentration to increase over time. Right? And the salt bridge here, like I said, is just doing its job to make sure that we can move charges all around in a complete electrical circuit. Right? Real quick clicker question. Which transformation would take place at the anode of an electrochemical cell? Pause. Think about it. Come back. Right, it's going to be A. The NO going to NO3 minus. Right. So in our galvanic cells, we're going to have two half reactions. One is always going to be an oxidation. One is always going to be a reduction. So for our zinc and our copper, we've got these two half reactions. Right. And they're going to combine into this overall reaction that we've seen here. So that's the chemistry that's happening with this previously shown electrochemical cell. Right. So we got the two half reactions. One happens at the cathode, the other one happens at the anode. So let's look at another example. So we got manganese oxide and iron, so our MnO4 and our iron 2 plus are present in the same solution. The electrons are going to be transferred directly when the reactants collide, and we can't do anything useful. The useful work is only obtained when the oxidizing agent and the reducing agent are separated to initiate electron transfer through a wire. So here they're doing it with manganese oxide and iron, right? So we can have now separated our two reactions, but we still have not completed the circuit. We're going to need something to do this. Usually that's going to be a salt bridge in most of these illustrations. We'll see that it can be a porous disc or something else that allows ion migration. Okay? So oxidation at the anode, reduction at the cathode. We've got two ways to separate those, either a salt bridge, so U-tube filled with a strong electrolyte held in a jello-like matrix of agar or something else, or it could just be a string with some saturated electrolyte. The key being that it's going to be a strong electrolyte. You don't want it to run out of charges. Or it could be a porous disc where the things are physically able to migrate from one side to another. Batteries actually use paper that is soaked in an electrolyte as the salt bridge or where the ions can transfer. So Let's look at this anode. The anode is where the electrode where the oxidation occurs. Right? Electrode, oxidation, anode, vowels. It is the electrode where electrons are produced. So electrons are emitted from the anode, all vowels. It is where the anions move towards the anode. It has a negative sign, right? Anions, negative, anode. The cathode is where the reduction occurs, right? It's the electrode where the electrons are consumed at the cathode, right? The cathode is the one that is getting larger over time, right? It's going to be the fat cat. So think about that. It's like fat cat. The cathode gets fatter, right? It is where that cations migrate towards, right? Cations move towards the cathode, and they all have that plus sign in there. It has a positive sign, right? So there is our red cat, right? Red cat. Cathode is red. And if you can remember red cat, anode's going to be the other one. Typically, the anode is made of a metal that is oxidized, and the cathode is made of the same metal as produced by the reaction. So if the redox reaction were running that involves the oxidation or reduction of an ion to a different oxidation state, so iron 3 plus to iron 2 plus, or 2 plus to 3 plus, or the oxidation or the reduction of a gas, we can use what's called an inert electrode. So an inert electrode is one that does not participate in the reaction, just provides a place for those electrons to jump on or off of the chemical species that you're interested in. So it can be something like platinum, right? Platinum is a noble metal. It's relatively inert. So you'll oftentimes see platinum electrodes. You will see carbon, glassy carbon electrodes, where they're taking some condensed form of carbon, and it's not going to be involved in the reaction you're looking at, but it is chemically pretty durable. This is what our salt bridge is going to look like, and a porous disc just kind of in the middle. You will have probably seen some of that porous material. It's just a ceramic, and it allows ions to go from one side to the other. It's going to allow ion migration, just like ions are going to migrate out of and into your salt bridge. Right? Cations are going to be going to the right, and anions are going to be going to the left. Galvanic cells consist of